make sure to record. Okay. So I'm just gonna erase this stuff here. Okay, so as far as like your first question about where do you start counting from or whatever, you can count from anywhere. Like for example, on here, right, we could count 1, 2, 3, 4, right? Or we could count, whoops. We could count 1, 2, 3, 4, 5. I guess I didn't finish counting the other one because I was done with the, let me see, 4. So this would be 5 and 6. There we go. But yeah, so you can count from anywhere, but the biggest thing is like, so in this concept, what it's talking about is like these large groups, right? Like these, obviously ethyls are like bigger groups. And do you remember back when we were talking about, oh God, chair conformation?
Yeah, the chair. Yeah, but so this is the thing I'm confused on though, is like, it doesn't 1, 2 imply that they're the big groups are on the adjacent carbons, and then how are you not getting a ton of like steric interaction because they're right next to each other?
Okay, wait, say that question one more time.
So if you have 1, 2, that implies that the big groups are on the adjacent carbons, like they're right next to each other. And if that's the case, then isn't there a ton of steric interaction because of their proximity?
Well, remember that you're gonna have some sort of something somewhere. Like you can't avoid every single piece of it, but what you can do is you can reduce it, right? And so at the end of the day, remember that the molecules, the electrons, everybody wants to be at the lowest possible energy state, and they will. That's what reactions are. Like reactions, chemical reactions literally are electrons from atoms, right, or molecules, but electrons trying to reconfigure themselves to get to a reduced energy state. That's all they want. All they want is to be like as low as possible, right? So, you know, and there are things that will overcome steric hindrance to be able to hold them in a certain shape, right? But
But
that's
like,
yeah, go
yeah,
ahead. No, go
I
ahead.
just don't understand what's so bad about 1, 3. Like, can you just go over 1,
Yeah.
2, 1, 3, and 1, 4, and then explain what makes some good and some bad?
Yeah, so okay, so remember, do you remember like with your chair conformations? So the way that I remember it is wherever your point is pointing, that's the direction that your axial will be. So this point here is pointing up, so our axial will be pointing up. This is pointing downward, so our axial will be pointing downward, right?
Mhm.
Like so that's
Yeah,
how
no, I
this.
remember that.
Okay,
Yeah.
cool. Yeah, and I'm gonna do these. I always hate the ones in the middle because I'm like, you always look so awkward. Like, okay, so anyway. And then we have our equatorials, which will be opposite of that. Don't get that one confused. So this one's up, so our equatorial will be down. Our equatorial will be up. Equatorial will be down. Equatorial will be up. Okay. And then so in this configuration, you just have to pick something. So we'll just say that dashes are into the page or down and wedges are out of the page or up, right? And so when we put this up, and let's make sure to add our double bond on there once we get everything situated. So, well, I labeled this initially just to like show something, but let me start over with that one. So we're saying that dots are downward, so out of the page. So this will be equatorial, which makes sense because these will want to be equatorial anyway. So let me get rid of that. So equatorial will be our ethyl, also known as your CH2, CH3, right? Just a little review there. And then your nitrile is on the next. So I am choosing, just for consistency, I am choosing this configuration. And I typically always start my chairs are always gonna I always start mine in the upper right corner. It doesn't matter as long as you're consistent. So, but I'm just telling you how I do it. 2, this is 3 and 4, right? obviously 5 and 6. So which would put our double bond. I'm just gonna put the double bond there just to show it's there. Okay, so anyway, so we're using orange. Okay, so and then also our other over here on the 4 will also be our other ethyl, right? And so obviously equatorial, those are the least, you want to put your, if possible, your largest groups on the your energy states away from each
Equatorial,
other.
right?
Yeah, exactly. Yeah, as far away from each other as possible. So equatorial, obviously, it's like stretching your arms out versus stretching them up, right? So then our CN, so and I just want to point out that this, remember, we have decided that dash means down or into, right? And so that means that wedge means up or out of, right? So this, our equatorial, is up, it's facing upward, right? And this equatorial
Yes.
is facing down, right? So I just want to show the
Yes.
consistency. And then we have our nitrile here and here, right? So obviously you're going to have some sort of steric hindrance, especially if you have something that's, you know, close to each other, right? But these are also equatorial. So remember that this is a ring, which means that our equatorial stuff is going out like this. So it allows for the most space possible, right? And sometimes it's hard to see that when we're on like a 2D or 1D scale. So so just remember that that would mean that our AT would be here, our CN would be here, our CN would be here, our AT would be here, and I'm obviously missing one, so we'll just put another one in there. But so that's kind of what this would look like, right? And then we would have our double bond is here conveniently where my other thing is. So anyway, so this is the least energy conformation. Now, if we had, imagine that we had now, if we did 1 and 3, right? 1, 2, 3, this would be over here. 1, 2, 3, this one. Particularly because these can flip back and forth. So let's just say that this now flips on the axial, right? And so you would have this here, up, down, up, and then you would have this, because they can change shape, right? They can change conformation. But if you had that, then they would both be on this axial and have this steric hindrance. So that's why 1 and 3 doesn't work, because they're both together. But now if they were, say they were both up, this up would be over here on this equatorial, right? So this allows for the most space possible. So that's why this 1 and 4 conformation, like 1 and 3, won't happen, because they're too close in that sense, right? Because then it would be over here, right? It would be over here.
Yes.
So, you know, so then if this was down, this would, you know, so anyway, so that's why that 1 and 3 does not work. And that's why you will see that as we get into this concept over here. So we've established that this rule applies, right? Like 1, 3 does not happen.
Wait, can I just ask a question though?
Of course.
How do you know that yeah, so like for the 1, 3 example, they're both axial in this case. Like they're both represented as axial.
Yes. So if you had like 1 axial and 1 equatorial.
Yeah.
So down, down, up. So this would be, our equatorial would be down, down. Right?
Like how do you know that the ethyl is I'm just like confused how you know that the ethyls would both be up, because isn't one sorry, what determines whether it's axial equatorial? It's not the wedge and dash. That's just as if it's up or down, right?
Yeah, so it's you're deciding when if you're drawing a chair conformation. Was chair conformation in OChem 1 or OChem 2? No, it was like,
it was 1. It was
yeah,
like
yeah, it was like way back in 1. Okay, let me just see if I just want to bring it up real quick so you can see also the
like I remember that you want it to be equatorial. I'm just saying, like, isn't
so
like
it's gonna be like whatever that atom is, right? Or not atom, whatever that molecule is, in that conformation, you can still have remember that like your atoms are moving around and stuff, so you can still have things change shape. But whatever they're on, like whatever side, like if they're up, then they're up. Like, so
Yeah.
when you
Wait, but
change
then
your conformation, yeah, go ahead.
can you go over though then why 1, 2 is okay?
Yes. Here's our confirmations. Okay, I found them. 1 second. This. There. Oh, I literally found the correct page. Oh, that was so lucky of me. So here is that. Interactions, right? One, 3 diaxle. So if it's on an axle, so so remember that we're talking about like interaction states here, right? So when you have this, for example, in this one, this is, these are your 1 and 3s, whoops. In here, it's your odds, right? 1, 3, or you could say that this was like your 5, but either way, like, because it's called a 1 and 3, we can just call these the 1 and 3s, right? So these interactions, so that's why you would want your least, your smallest, like energy, what am I trying to say? Steric hindrance. So every other, the axial will be pointed in the same direction, right? Every
Yeah, no,
other,
so I know that,
okay.
but I'm just like what prevents the two groups from being on 1 and 3 and having one axial and one equatorial?
Well, that has more to do with like the molecule itself, like whatever it is that, whatever it is, right? And so if like this concept is what would prevent that from forming, if that's what you mean, like when you're forming something and it's going to go to the third one, right? It's not going, if it has to do 1 and 3, it's not going to be on that axial because they're all the same. Like it's not going to form there
Yeah,
because of
got
the
it.
high energy state. So it literally just, it won't happen because of that steric hindrance, which makes it, the electron strain, high energy state,
Yes.
all of that.
Yes. Wait, so then can you go over 1, 2? And
Yes.
yeah.
So as far as like why it's allowed, is that what you mean?
Well, just the concept that 1 and 2 are closest in proximity. So why is
Yeah,
that allowed and 1, 3 isn't? Like, why
because
is that better?
they're opposite of each other. So as far as like axials will be opposite of each other, they point in opposite directions. And then if we had this as a circle to represent our equatorials, they would still have like this, right? They would still have like this space here if they were on these equatorials. But again, one is going to be pointed upward, which is hard to do on this, and the other one's kind of pointed downward. Whereas these ones, this would also be kind of pointed upward. It doesn't look good, but hopefully you
No,
know.
I understand. I follow you though.
Yeah. So these are, both of our equatorials will be in the same direction. Both of our axials will be in the same direction versus ones that are right next to each other. Because of this shape that we have, it forces these away from each other.
Yeah, I see.
Because if you're looking at it on a plane like this, you would have one equatorial here. And let's just say we're looking at it just so that we have 2 carbons, right? So this is, this is carbon 1 and carbon 2. This is carbon 1 and carbon 2. Well, I guess it should be the other way around if I was using the same carbons. So 2 and 1. Okay, so how this has the axial up and then the equatorial down. So this would have the axial up, axial down, and then we would have this equatorial kind of upward and this equatorial kind of downward, right? So there, or you could, put it in this direction. Obviously this is like, again, 1D, but anyway, they point in these opposite directions. That's the point. That's the major point here. They point in the opposite directions. Obviously equatorial, you're away from each other regardless, but because you can have this conformation shift, they would be on the same axial plane, like upward, because it's not always that like, okay, this is the shape of, did I draw this correctly? There we go. This is the shape and it's never going to change shapes. Remember, we can also point it downward, right? That was the point of showing that, with let me see, like this. Sometimes my chairs get funky, but anyway, hopefully you know what I mean. You can flip it, right? So this point is over here and now it's on the bottom. The same point is over here, right? So you can flip it. But that was the point in seeing that with the models, right? Is that you can see how they shift and how whatever your substituent is, whatever your group is that's on it, can move either from an axial or an equatorial, right? So it's not stagnant is what I'm trying to say. It's not always going to be like, oh, okay, like 1 and 3 have these like huge groups on there, ethyl and, T-butyl. Okay, well, it's going to stay in this because that's it. They just won't be here over not shifting shape of the molecule. Does that make sense?
Yeah, no, I see.
Cool.
Okay.
So that is why. So we'll go back to this now. Okay. And then, so does that answer the question about why you would need to flip this, because this would be a 1 and 3 thing?
Yeah, no, I think I get that. It's just that I'm trying to find a specific example, but in some of them from last week, like you see how like the CF3 is in that position. So sometimes when you like, aggregated the molecules together, if you will, to form the ring,
Mm-hmm.
the CF3 remained in that top right position, if you will. But then sometimes it went to like the bottom right position. Like sometimes it like changed.
Mm-hmm.
And I don't know, I didn't know
Did
why.
it have a group here like this?
I'm trying to find the example. Let me see.
The only thing I can think of maybe that it
Um,
has to do with is that like Diels-Alder thing where you're like, where you have your, your rings like this, and then your rings like this, and it like these bottom rings attach to the top rings. But like even that doesn't really make sense because you still have this ring here. So
yeah, I'm trying
is
to
it, let
find.
me see if I can also get on there. So let's see if something works right. Conjugated systems?
Um, mm,
No.
sorry, I'm like
No,
really
you're
like
fine. I'm looking too.
disorganized.
No, you're fine. You're fine. You're fine.
No, it was just in the section about
Diels-Alder.
yeah, that
Okay. Um,
I'm looking through it right now.
are you talking about, I see one, I'm just gonna scroll down here to the bottom. Hopefully I have a blank page. So I see one where you have, let's see, MEO, sorry. Um,
Oh, I found one sort of. But go ahead with that example and we can come back to the other.
well, the only thing I was gonna say about this one is that, for this, it wouldn't matter if you flipped it because this is symmetrical. This is a symmetrical. So that one wouldn't matter. I do see number 16, although I didn't look at it yet, but no, that one does flip as well. So
So for example, there's one, what page is this? I think this is page 12. There is one that has,
In which section?
it's still the Dials Elder, I
Mm-hmm.
believe. Yeah, I don't know because I had just taken a picture of it because I
No,
didn't
you're
know.
fine. You're fine. I just
That's
want to
why
make
I'm
sure
not sure.
I'm looking at the right thing. So ethers, organo, no wait.
There's one that's like example in parentheses with actual donating and withdrawing groups, and there's a NH2
Is
on
this
one.
conjugated systems? Where is this? Aromaticity.
Here, I'll find it real quick. Let me just get the book.
Okay, page 12. Okay, I see diene and dienophile.
Yeah, go to page 12, first example, top of the page.
Oh yeah, okay. Uh-huh.
So in this example, do you see how the second part of it, if you will, has the COH on the bottom?
Uh-huh. Yep.
And then when you go to form the ring, she says
Flip it.
1,2 major product, and the COH group is now suddenly on the top. Like, how did that, or like, why? Or like, how did that happen?
Well, because otherwise you would have formed a 1-3.
But like, how does the group just like go
Okay.
to the top?
Okay, remember that these are just molecules in a solution, flying all around, doing their thing, switching away, doing this, doing that. They're not this, they're not waiting around like, hey, I am parked just like this, and I'm not gonna move. And whenever you're ready, you just come up on here and we'll connect in this exact little perfect scenario, right? Like, gotta think about this in terms of like entropy, enthalpy, things just flying around in all different sorts of crazy ways, right? So this is 1, 2, 3. I just want to make sure I was labeling that correctly, right? And so if we attached it here, then we would have this giant group and this giant group on a 1-3 conformation. So this just, again, it's not gonna occur. So what happens is,
Yeah.
so what happens is this molecule and this molecule right, that's right, yeah. This molecule and this molecule, like it will come together in this conformation. Right? So it's not going to, this will not approach this in this while it's like this. It's going to wait for this thing to, imagine flipping around through the page or something, right? It's going to approach it from this direction.
Yeah. Okay. I see. Oh, can you go to the next example, the one right below that?
Yep.
So in this case, can you explain why you don't form a 1,2 and why you only form a 1,4?
Because it wouldn't be a 1-2. What do you mean?
Like why is that?
I'll show you. Because you're not counting your carbons.
Oh, I see that double electrons in the double bond will form another one and then it will be a 1,3.
1, 2, 3. Remember, this is the bond here.
Yeah, I see now. But okay, but I have a question though, because um the pair of electrons that's currently like being donated to form that dash bond, um now that those are gone in essence, like not, in that double bond, doesn't that make room for the CO2 CH3 to attach to the carbon number 2, if you will? And then that would be a 1,2.
Trying to understand. So
Yeah,
these, because I think you're just kind of confusing so these electrons here
right.
are going to move here to form this bond here.
Yes, exactly. So now, Yeah, so now that that's happened, carbon number 2,
Yep.
like, wait, yeah, wait, no.
You figuring it out?
Wait, actually, I think I figured, so wait, on carbon number 2, there's like 2 implicit hydrogens. Yes.
No. There's a double
Why?
bond here. Oh. Yes. Okay. Yes, I get what you're saying. This here. Yeah.
Okay, yeah. So I was saying, okay, yeah. So the CO2 CH3 cannot move there because there's no more octet, like octet is full.
Yeah. Even
So then
so,
so it
like,
has to move to the 4th position. That's how you know.
but this is not transferring to this carbon here. That's not what's
Oh,
happening.
okay, yeah. Wait, that's what I thought was happening.
No, what's happening is there's no transfer of things. And even if these hydrogen weren't there, this wouldn't transfer onto here. There's no transfer of things. What's happening is this tail, imagine, is coming out of the page and going this way and then aligning on this side. So now you have number 4 here, right? So imagine just
Okay.
taking this tail and flipping this whole thing around. And that's where you get that bond.
Wait, but
Whoops.
if the molecule is flipping like that and you're getting then that's not number 4 anymore.
Exactly. You're right.
Oh my gosh, I'm so like,
You got it? Yes. It's
yeah,
not
okay.
number 4 anymore, right? It's
No,
now
yeah.
number
No,
3.
you just
I was
explained
saying
it
4 just to
perfect.
show that it was moving up there. But
No,
yes, right.
yeah.
It's not number 4 anymore because the
No.
numbering is just arbitrary to whatever you're trying to do, right?
Yeah, yeah, I see totally. Yeah, okay.
Listen, it's not, sometimes it's really hard to like visualize because we're talking about things, we're trying to like put, 1 and 2 dimensional characteristics on something that's like doesn't even really exist in real life, like it does, but it doesn't. Like you can't, electron clouds are not like solid matter that you can measure in a traditional way, so it's hard. Like we're asking you to think about these probabilities of electrons being in a space, and we're representing them with 2 lines on a piece of paper. So don't beat yourself up over it.
Mm-hmm. Okay, wait. So then for the example right under that one, where it forms the 1-2 product,
Yeah.
can you
Erasive. Yeah.
draw the bond for me? Because
Are you talking about
yeah,
this pentane?
uh
Are you talking about the
ye
pentane? Or,
no,
oh no,
no, it's
you're
literally
talking about, yeah, I see
the
it now.
one that's like 1 chiral center.
Yeah, this one.
Yeah.
This one, right?
Mm-hmm.
So your bond formation, you have, I'm just getting a different color. Carbon 1, carbon 2, in this orientation, carbon 3, carbon 4. These other ones don't really matter so much, but I'm just doing it for completion. If we choose to flip this over, we would have 1, 2, 3, and then these all say the same, 5, 6, 7. Whoops, 4, 5, 6, 5, 6, 7, right? So that's what we're doing. We're flipping this over. Now, I could draw it like this, but that's not really what's happening, right? Because this is a 2-dimensional situation. So what's really happening, to make it more clear, is we have okay. And then we have this. I'm missing no double bond. Let's see. And then we move these here. Whoopsies. We move these here. We move these here. Move these here. And we end up getting this and, well, sorry, we end up getting, because we have these chiral centers, we end up getting this. Right, whoops. So we have this 1-2 product. So there's 2 chiral centers in this one. Or is this the one you were talking about? I thought you said 1 chiral center. This is the one you were talking about, right?
Yeah. Yeah, no, that's the one. Oh, yeah, I was just saying the one chiral center paragraph or line was above it, so you could find it.
Okay. Sorry. Yeah. Okay. Yeah. So, so that's where the bond. So you would flip this one over, right? Your dienophile. You would flip your dienophile over, and that's how you would get it up on top, right? So
how do you wait? So how do you know that it's going to be a dash for that oxygen group?
That's what I was just gonna say, because I knew you were gonna ask that question. So, so let's draw our axials like this, right? And let's draw. I always get confused with these ones in the middle. They always mess me up. This, okay, there. So now if we have we've decided we have a 1-2 configuration, right? So they both need to be going like in the same direction for, I mean, you could have also chose to, like, you could have also just done this, right? As long as they're just going in the same direction, either up or down, into or away from, right? Because if they're here, we have ME, and they're here, we have ME, versus, or if they are, you know, both down, we have ME. Oh, I'm sorry, not ME, down, that one, sorry. That was my bad. Whoa, that thing was huge. ME, sorry about that. Let's see. COCH3, right? Or we would have COCH3, right? So this would be if they're both in the same direction. Now, if they're opposite of each other, see if I can get my chair drawing practice in today, I tell you. Hopefully they'll get better as we go and not worse. Although no guarantees on that, but okay. And then I did blue for these ones. So this is down, up, down, up, down, up. Okay. Now, if we did opposite, we did ME and COCH3, right? These ones are, oh no, those are the same. Sorry, I did it again. Wait, let me see. COCH3. That one's not so much a problem, but these ones would be more of a problem, right? Because they're in the same plane of each other.
Yeah, I see.
Yeah. So that's why we do them opposite, because it reduces the energy, right?
Right.
So it's not that it couldn't exist, right? But if we have the option on a 1-2, we kind of want them to go in the same direction, so that way we reduce the energy on them. So they're just further away from each other.
Yeah, okay. No, I see. Okay, and then as just a general question, how do you say it? Dies alder deals?
Yeah, dials alder, yeah.
Dials?
Deals,
Yeah.
dials, yeah.
So yeah, for that topic,
Yeah.
I just want to make sure. So when somebody says a dials alder reaction, that's simply just saying it's a cycloaddition. That's
Yes.
it. Okay.
Yes. Yes.
There's nothing else that's special about it. It's simply just that these two things like coming together to form a ring.
Yeah, yeah, it just some sort of like, you know, a cyclo addition, right? It's Diels-Alder reaction is just some sort of cyclo addition, right? And then, you know, we
Yeah,
call it our diene and our dienophile to identify the different pieces of it that are coming together.
yeah, but then so why is it that there's like the designate, I think it was for this concept, right? It was the designation for like if a group is on the outside or the inside to make it a wedge or a dash. Like,
Uh-huh.
can you just explain? I mean, I don't know if that's just like a what do you call like a rule you follow for lack of a better term, but like is there something specific reason why like outside means dash and inside means wedge, or like
No,
is it
there's no, it's not like you have to do this or you have to do that. You just, it's arbitrary until you make a decision. That's not arbitrary anymore. Right. So inside or outside more just has to do with like, are you deciding, is this? Oh yeah. I thought there was another example. Let me see up here. Well, I guess maybe for like these is this like this is like another example of this, right? But no, not these so much. No, it's the ones down here. Okay. It's like these ones down here, right? The wedges or the dashes. I thought
yeah.
we also went over this in another because I thought I had more examples in this. This isn't very many. Let me just look. Those are the conjugated systems. This is all on conjugated systems, right? But I had more
Yeah, no, like you like explained it well. Like I understand now where I was having confusion before. But like the other thing is, yeah, so can you go over the like supra thing and
yeah,
whatever
yeah,
that
yeah,
thing?
yeah. Yeah,
Okay.
absolutely. Yeah, no, sorry. I was just looking to see because I thought I had more examples. I also found where I don't know if you were there in the beginning. I thought I didn't have the whole like thing uploaded, and I guess I just uploaded it in the wrong spot. So anyway, I like took 10 minutes in the beginning of the office hours, but
No,
okay.
yeah, I know. I saw like the first like hour and a half of it. So like I saw a good amount.
Yeah.
And
Yeah, no, I thought I had like not uploaded something in it and I actually had, but I'm just now finding it.
yeah.
But anyway, okay, so with these um well, this is like the wedge or the dash, right? So this just has to do with gosh, I just thought I had better examples, but maybe I only have these examples. So this really just has to do with like what direction is it pointing and then like how are you going to know how it's moving together, right? And so like with this, we're just choosing whatever they are. Like like we just kept choosing that these were, but these could easily have also just been all dashes, right? So it doesn't necessarily matter. Um, but like what has to do with it is with these ones, pay attention to the stereochemistry. Um, with these ones, it's like where like are they, what direction are they pointing, right? So we've decided that anything outside of the ring is a wedge in these examples, right? We decided that anything outside of the ring was a wedge, and we decided that anything inside the ring would be a dash, just to show directionality. It wasn't that like it has to be that way. Like we could have easily have said, okay, I'm deciding that, you know, anything that's outside the ring is dash. So then we would just put it like that. We would just dash them all. But there's no rule that says it has to be this way or that way. It's completely arbitrary until you make a decision, and then it's not arbitrary anymore. And you could, if you wanted to, like I could say in this one, like, you know, out is wedge, and then I could say in this one that out is dash, because this is an entirely different problem. And so it doesn't necessarily matter, although I don't suggest doing that because it's good to just stay consistent. That way you don't make, you know, a stupid mistake on your exam because you're just trying to be funny, right? Like you're just trying to like try out all the different ways to do it, unless you feel really comfortable with the concept. But you know, I would just say like just choose something, and whatever that thing is, just stick with it, right? Uh,
Yeah.
So yeah, so and then like in this example, right? Let me just get rid of some of my writing here so that you can see that this is out and this is in, right? And so, it's kind of in, but it is in the sense of like with your diagonal file, if it's pointing basically toward the ring, sometimes it's easier to see versus away from the ring, right? Something that's away from the ring is going to be out, right? And I thought we had another example of it, but I guess we ended up drawing it out because these two were opposite of each other. But like this is kind of a little bit easier of an example to see that it's inside the ring because our ring would be formed here. So that was something, our ring would be formed here. That was something that I sometimes had trouble with the diagonal file is like, I'm like, oh, well, technically that's not inside the ring, so that's why I had mentioned sometimes it was a little bit easier for me to think of like for these diagonal files, is it away from or is it towards the ring? Because if it's towards the ring, then it's inside the ring.
Okay.
And that will, and you could use that same concept for this too, right? Like this is away from the ring or is this like inward towards the ring, right? Like it's going.
So yeah, so for the CN that's on the bottom, so that one's like outside, but it's also in. Yeah.
Yeah, so what did you say? Sorry.
So it's outside, like it's pointing out, like, if we're looking like vertically, it's pointing out, but it's also into the ring.
This was that they're the same molecule and it wouldn't matter in this example how you drew it. It could either be this here or you could draw it this way and it wouldn't matter because this doesn't have anything to define it. So you could say that it's either this way or that it's that way. Because these are arbitrary, there's nothing to define it. And this doesn't have any substituents on it to confirm whether a wedge or a dash is inside or outside the ring. That's why.
Yeah, I guess like my question is just like, how normally it's like outside means dash and then inside means wedge. But that example with the CN on the bottom, it points outside. And so like,
are you talking about this example here?
I'm talking about like you see the yellow drawing, the first yellow drawing you did where you were pointing to
this?
Yes. And then do you see the CN that's on the bottom?
This?
No, like it's still in yellow. It's simply just on that. Yes, yes. So that one. So it's pointing outside, right? Like
no, that's what I was saying.
No, but like it is like it's pointing out and into the ring. Like it's like both things. Like it's like pointing down, but it's also pointing into the ring.
Down, yeah, like you mean like as in like this line is pointing downward and this line is pointing upward, is that what you mean?
Yeah, so like does the up down thing have no bearing on it? You simply saying like it's pointing to the left, therefore it's into the ring. Like that's
Yeah, kind of like, because how else would you, let me ask you this, I just want to get rid of some of these lines here. Let me just get rid of some of this stuff.
Because when they said outside, what that means to me is it's pointing downward. Like the ring essentially is relative to that bottom CN, the ring is above. So to me, when I look at that, I still think it's pointing down.
Yeah.
Yes.
That's why I said, because I too struggled with the dieno file and what outside or inside was. For the dienes, it's very easy to determine what is inside and what is outside the ring, right? Like this is clearly inside the ring. This is clearly outside the ring, right? Like dienes are very, very easy. But when it comes to your dieno files, it's a little less intuitive for me because I'm like, well, these are our main, our backbone carbons, if you will. And this versus that, well, technically this other bond is going to come in here. And so they both look outside the ring to me.
Right. So
that's
yeah,
why I was saying with the dienophile, sometimes it's easier to think about it if the substituent is pointing away from the ring that will be formed, right? Then it is out. And if it is pointing towards the ring, right? Even though, like, don't think about up or down, but just think left to right.
No, I get you. I understand.
Yeah, I know. It doesn't look, the drawing, again, this comes back to, we are trying to confine chemistry to 2D drawings on a page or on a computer screen. So it does present a challenge, and I understand.
But yeah, but then even with the one that's pointing in, so in this example, it's showcasing that the wedge and dash is arbitrary because, right? Because typically when you say something is out, the gap note said it was a dash. And when something was in, if you will, they said it was a wedge, but then in the product, you see the reverse. So is that just like highlighting that it's arbitrary or like?
Yeah, it really is, as long as it's consistent throughout the problem that you're doing or the molecule that you're creating, as long as that is consistent, it is arbitrary. Like I said, though, sometimes it's best for you as a student to choose a system and stick with it.
Yeah, no, I see. No, thank you for, I'm sorry to have you repeat that. I just like,
No, it's fine. No, those are like, these are all things that I tripped up on too. Like, I was like, this is outside the ring. What are you talking about? And it's not until I come back and, teach it to you guys that I'm like, oh yeah, I remember. I struggled with this too. I was,
yeah.
some people, like, they go back and listen to like the old, like, organic chemistry office hours that we had with Dr. Pillai, like, when I was a student, and they're like, oh, you're the one from the office hours. I always remember here, because I, like, always was asking questions, always, like, I was you.
Yeah.
It's good
No
to be curious.
problem. No problem. I will happily claim the torch. Passing the torch to you. No issues there. It's okay.
Totally.
So yeah.
Yeah,
Okay,
so
wait. So now can you go over the thing about the Supra stuff and whatever?
yes. No, 1 second. Sorry. Okay. So then the and supra intra. Okay.
Yeah.
So I don't think I put anything else on here. I know it's an example of it, but I'm trying to think if I actually, like, put anything on here that has to do with supra and supra intra. I gotta see. From last week's stuff, right? I don't think I did. I think
Well,
last
yeah,
week
because in this week's stuff with the aromatic, there were comments about like, let me find it.
yeah,
Um,
it's all good. Let's see. I did not. Yeah, I think I ended my gap notes right before some of that super interest stuff.
yeah, so for instance, from this week, if
Yep.
you can just maybe like explain it in this example if that's helpful, like in page 4 of aromatic stuff.
Yeah.
Yeah, so she says suprafacial gives continuous cyclic Huckle
Yeah, Huckle.
transition state. So yeah, so can you explain like how you know that, like I just don't understand the connection between the suprafacial and the Huckle, I guess.
Yeah. Let's see the
And I
Huckle.
think it's because I don't really know what suprafacial means.
Yeah, no worries, no worries. Yeah, okay, so this is what you're talking about here,
Yeah,
right? This page?
yeah.
Yeah, page 4, yeah, okay. So, okay, what is the part that you said that you were specifically asking about? Where?
Do you see in red when she says suprafacial gives continuous cyclic? Yeah.
Yeah. Okay,
So can
so
you like just explain that whole thing?
yeah. So this is So this kind of goes back to molecular orbital stuff, and I'm gonna put it up here. I'm gonna put it underneath this, but I just want to see if there's any examples in here so I can piggyback off of it. Not really anything of value for this explanation right there, so I'm just gonna do this. Okay, so this kind of goes back to like wave function stuff, right? So there is either, so let's just take let's take a, because this is obviously we're doing cycloaddition, right? So let's take a 4-carbon system, right? And then we'll take a 2-carbon system. And then, so remember, I think the only thing that I had like written that might have been somewhat useful was this little chart here that I wrote. Oops. Let's see, this little chart, where is it? Right here. This little chart about the and the 4n plus 2 super antra versus super or antra, right? So depending on how many electrons are involved in the reaction, determines the amount of nodes that are a part of, right, that are a part of the reaction, and then so that would determine like what kind of addition it would be, right?
Yes.
So because the nodes, remember, they change our anti-bonding and bonding, setup. So we have, so let's just say we have we have to have at least 2 nodes, right? But so let's just say we have our 2 ends, because that's really all that matters, like the sets that are coming together, right? Like A and B are coming together and C and D are coming together, right? So those are the ones that matter, right? So if we had ones where it was set up where you had these where they were coming together like this, what happens is these ones align this way, right? And so this would be, and obviously these are all connected as well, right? But this is how these would add into each other, right? So they have this supra, and you could also say that they right, you could also say that they're colored in here. Does that, right? So they can still come in this direction, right? But the point is that they're lined up, right? Their bonding and anti-bonding are lined up in a way that allows for bonding. Okay, when you have, so this would be considered a supra, because both of the ends here are the same across the board, right? Now a super antra, let's say we have these, and you have, maybe you just have one, right? For this one, we'd have to have whatever, but let's say you just have one node, and so it switches like this, right? And then so this one has 0 nodes or whatever, so you would have this switch here and say that this one also has 1 node. So then you would have something here, and you would have, oops, sorry, I messed that up. I'm like, why does this not look right? There, you would have something here, and you would have something here like this, right? So you have these nodes, but again, these line up in a way that allows for bonding because they're the same, they're on the same, they're in the same, like, bonding and anti-bonding structure. So it allows for this to happen, right? This would be considered a supra antra because they're in different conformations, right?
Wait, why are they not both antra though? Because the top
sorry.
pair.
Yes, you're right. Sorry. Antra. Sorry.
Okay.
No, you're right, you're right. I'm like, wait, what's the other one? I'm missing one. So antra, right? So
Yes.
then, thank you
And
for,
then the supra antra doesn't happen, right?
well, the super antra is where you start to find your Mobius loop, right? Because you have these, so here we see, well, these are 4, right? So this is a 4 bond. So this one's, so, okay, so there's the molecular orbital stuff. So now we can kind of start to look at this, right? So we have these where these are all set up on the same plane, right? And so we have this bonding happening in this ring, right? So that's how that stuff is happening. This is supra, right? So for this, we're not going to see this for this 4 bonding because it's anti-aromatic. So so even though they're both supra, it's anti-aromatic. So you're not going to see that. It's you're not going to see that conjugated system, right? Anti-aromatic. Those are forbidden in the Huckle systems. So then
But
when
when do you, oh, sorry to interrupt, but
you're fine.
when do you know when you do the from last week, the like it was called like dis or con, like it's like the rotating
Dis
thing.
and conrotatory, yeah. So that depends on how many electrons are involved in your system. So if that was this up here that I was
But then why was that example not a candidate for a dis or con?
so you have conrotatory, which is a supra antra. This is what's allowed, right? So
Yeah.
um I'm gonna write this down on the down there so that way we can look at it. So okay. So now down in here, right? So for these, our 4N system are our conrotatories, and what's allowed is supra antra. Our 4N plus 2 are our disrotatories. And remember, conrotatory and disrotatory just tells you which way it rotates when it's doing like,
Yes.
opening or,
Yes.
okay, yeah. And then, so these are supra, and antra, right? And so we'll find that.
Wait, I'm sorry.
There it is.
Just one more thing before
Oh, you're
you.
good.
Okay, so I know the rules like with the Huckle stuff with the 4N and 4N plus 2, like if you have 4N plus 2, you're getting the aromatic if it's Huckle.
Mhm.
But why does that indicate that it's disrotatory?
Uh, what do you mean,
Is
4N
that just
plus 2? Or the
yeah,
conrotatory and the disrotatory has more to do with your like your ring opening. So like it has
I just don't know how you automatically know that 4N means con and
it's just
4N plus 2
it's
means
just a
dis.
concept that you know. It's just a
Oh,
concept that they
okay.
tell you that you know, like 4M plus 2, those are disrotatory when we're doing like the ring opening and closing, the electrocyclic ring closures or opening if we're trying to open them up again, right? Is like this is just concepts that you know of.
That you memorize, basically.
Pretty much. Pretty much.
Okay, because I thought I was missing some underlying reason. Like,
No. It's just there probably is a reason. Like I just don't know what it is.
yeah,
So
no, understood. Okay.
yeah. So for me, it's you just know that.
Yes.
But
Okay.
maybe in like some higher up classes, they probably tell you, or but I'm sure if you reach out to the professor, she would tell you.
Yeah, no, okay.
Yes. Okay. So with this one, so we have here, we have 6 electrons. This is whoops. This is a 6 electron system, and our
Wait,
four.
so those are the rules for, I'm sorry, I
Oh,
interrupted you
you're
so.
fine. Go.
Okay,
Tell me.
wait, so those are the rules for Huckle, though. They are not the rules for Mobius.
Yeah, we're getting there. We're getting there.
I was just making sure.
Yeah. We're getting there. Yeah.
Okay,
Yeah, no. So we have our Huckle rules, and you'll see like that. Like Mobius is basically just the opposite of Huckle. Um,
right.
well, and this explains the opening and closing, right? This twisted versus, so this explains like this conrotatory and disrotatory thing, right? And it has to do with like their transition states because these are your antis, right? Your super antra. So anyway, so this is, so anything that's this is 6 electron system, right? 2, 4, 6. Those are the 6 electrons that are participating in this reaction. So that's why this has to be a super or an antra, right? So these are both supraficial. So our orbitals line up, right? Bonding and antibonding orbitals line up.
Yes.
So this one, in this cycloaddition, we have, this is a 4 electron system. This is why a Huckle transition is forbidden, right? A Huckle transition does not allow for this to happen, right? So because it's a 4 electron system, we said 4n has to be super antra, right? So it's anti-aromatic, high in energy, so the reaction is forbidden, aka it won't happen, right?
But why can't it happen with the Mobius?
It can. It will. You'll see. You'll see. We'll get there. See, Mobius transition state.
Okay.
Patience, my friend. So again, 8 electron system, right? This is a 4n, right? Forbidden. Okay. We're specifically talking about the Huckles right now, right? We're specifically
okay.
talking about the Huckles right now. That's where
Yeah.
we're starting, right?
Mhm.
So next, try supra antra addition, right? So this is where we start getting into, this occurs via Mobius transition states, right? Where the transition state goes through an atom, right? So versus, right, up here, we're talking about Huckles. Where is it? The Huckle rule, right? So it says right here, 4n plus 2, Huckle, right? 4n
Yeah.
plus 2 for the Mobius is anti-aromatic, right? 4n Mobius loops are anti-aromatic, right? So it says in here that this is the way in which it will, the Huckle rule applies to both stable molecules and transition states, right?
Yeah.
So
Can I just ask one question? Sorry, before
you
you
can
move
always
on.
ask questions.
Okay, but the thing is, for the example, for the one that's right at the top of your page, like don't like where you are right now.
Here.
So yeah, so it tells us that it's a 4s and a 2s, but if they didn't give you that information, how do you know by looking at that molecule that we're talking about supra? That's what I don't understand.
Like supra versus antra.
Right, like yeah, because like your understanding of like that molecule is really important for understanding if it's aromatic and if it's allowed. Like, how do you know by looking at it?
So your homo and your lumo, right? That tells you how many nodes there are. So in this, right?
I get what you're saying. I get it. You count how many electrons participate in the reaction. Then you label like you do the pi orbitals. You figure out where your HOMO and LUMO is. You figure out how many vertical nodes you have. Then you figure out from there like there needs to be a pair here, a pair here. Like that's how you do that.
That's why we do
Yeah.
this before we do this next part, right?
Yes. Okay. Yes.
Cool. Now it's clicking. It's coming. The concepts are falling into place, right?
Yeah.
All right. All right. Hey,
This is
listen.
why these office hours are necessary.
Listen, it comes with time, it's practice, right? So, with this, we know that we have 1, 2, 3, 4, 5, 6, right? Oh, it's 4 for this one.
Wait,
Right?
sorry, just one more thing though.
Here you go.
On that point, the other thing I didn't understand with regarding the electron p orbital energy stuff, is that it was only in Huckle, I believe, where no, actually no. So how that thing with the HOMO and LUMO, like the electrons, like if you had 6, like 2 of them went in P1, 2 of them went in P2, 2 of them went in P3.
Uh-huh.
But if you go to page 2, she
In
was
complicated
going
systems
over
or
no of like what we're on, like the aromatic stuff, like this same gap notes.
Mm,
Yeah, like right.
This,
Uh,
I don't have the page number on here. Let me see.
yeah, right there. Like
This?
that's a fine example. Yeah. But do you see how like in this example, the electrons like if you had four, for instance, then two of them would go in P1 and then one would go in each of P2 and P3. So it's not as like clear cut as the HOMO and LUMO is in figuring out how many vertical nodes you have, right?
I like this. Whoops, sorry. It's not doing anything. This is different from if we were trying to figure out nodes from each of these pieces.
Oh, it is. Okay, I didn't know
Yeah.
that.
Yeah,
It was
yeah. So this is an entire system here. This is an entire system, or this, right, is an entire system. So this is just showing like we have, it says right here, right? We have 6p atomic orbitals. We know that we have, this is a conjugated system, assuming that this is what we're talking about, but yeah. So anyway, we have a conjugated system. I think it's just an extenuation of this, but anyway, so, you know, 1, 2, 3, 4, 5, 6. So this is why it's saying that this is lower in energy. It's lower in energy for it to be cyclical versus linear, because see how this is where our lowest energy state is, which is slightly below where the third pi would be
yeah.
in a linear system.
But like for the purposes of determining supra and like anti,
So yeah,
you
so
use
okay, so what
HOMO
we
and
would do,
LUMO.
so let's just say that like, let's say that this was a 4 and this was a 2, right? That means that in our, let's just label this A and let's label this B, right? So we get to decide. So we have 1, 2, 3, 4, and we have 1, 2. And there's 4 in this one, right? Which makes one node, and there's 2 in this one, right? Which means 0 nodes. Because we're using our, well, oh, whoops, sorry. This would also be one node. This is HOMO, LUMO, and then, so we would have, with this one, this is all for A. Just draw it all out. For this one, we would have, we have one node, so it would get, because we're gonna use the, HOMO versus if we use the LUMO, we do that. So one node, so that means, say this is on top, top, bottom, bottom, right? And then if we had this that had, because it would be here, here, here. No, this isn't a conjugated system, but well, and then we would have we have 2 pi orbitals, 2 electrons participating. So 0, 1. So we would have our LUMO. We have to have one, or you need to choose a HOMO in one and a LUMO in the other, right? Because you need to have an unoccupied molecular orbital and an occupied molecular orbital that come together to create that bond, right? That part makes sense?
Mm-hmm.
Okay. So then we would have then these that would also have one node. And we would, because we want to make this work, we want to see if it's possible to make this work, we would just
Wait, sorry. On that point though, but aren't you making a bond between like the two that have the electron? Like in the like shaded ones you did though. Like when you go to make the bond, you draw it between like the shaded of one and like the shaded of another. So isn't that they're both housing electrons, right? So wait, what was the thing when you said like one is between an unoccupied molecular orbital?
yeah, so you have these you choose, for example, I want to bring up an example that we have. Was it this one, I think? Yeah, so like in this example, right, we had I know it's very messy, it's kind of hard to see, right? But like you have a couple choices. You can either do so, and then so here's the other, okay, let me just do this first, right? So with this, you set this up. This is exactly kind of the same in the sense, well, you'd have like one more here, right? But you can choose to do in this one, you would choose to do two. Yes, you have to have your HOMO and your LUMO one of each, because one is an occupied molecular orbital and one is an unoccupied molecular orbital. But remember that the shading doesn't necessarily mean that that's where they are. It just means that one is bonding and one is anti-bonding. And you need your two bondings to come together, or your two anti-bondings, right? But you need your two bondings to come together to make that bond, right? So the shading just has to do with where, because this is an unoccupied molecular orbital, it just means that it's in an alignment that could accept the electrons, not that there's actually electrons there.
Yeah, okay. That I wasn't getting that distinction. Okay, thank you for
Yes.
going through that.
Yes, yes. Yeah, so it just means that you have space for, because they need to just be aligned into whether or not they're bonding or anti-bonding. That's all the shading means.
Understood. Okay.
Yeah, you have to have one homo and one lumo. Well, the other way around, one lumo, one homo, whatever. You have to have those come together because one has electrons that it wants to give, right? And this one has 0 electrons, but it wants some to make that bond.
Yeah.
Right?
Okay. Yep.
Cool. So that's how you would decide. So this, you know, that this could happen because this is an but these are two antibondings that come together, and these are two bondings that come together. So that means this is allowed to happen, right? So then moving further down, we were in this piece of it, right? So yeah, so that's how you would like decide if this was super antra. So anyway, it's allowed, right? So these have 1, 2, 3. Those are your double bonds that we start, that, you know, move this bond here, this bond here, this bond here. That's how you end up with, there'll be a double bond there. Versus these are 2. So we've decided that anything that's in the 2s system has to be super antra, and super antra does not work. Anything that is, where is it? Whatever. Okay, right. Well, I mean, it's the same thing, right? But 4n plus 2 electrons are in the Huckle loop are aromatic, right?
Yes.
So that means that it will work. It's least energy, right? Low in energy. So it's allowed in a Huckle loop. Huckle loop, all that means is that there's no twisting of these p orbitals. Nothing is going through the Mobius, just means that the energy is going through the atom. So this is what we see here, right? So this is Mobius. So it's bottom to bottom, and then it's coming up through the atom and going top to top, right? So that's that Mobius loop thing, right? Versus over here, right?
Wait, so yeah, so that line you just drew, so you're saying that's where, wait, can you, whatever you just said, can you just say it one more time?
Yes. And let me see, this is also,
I just want to know that line you just drew, that purple line, is representing what? Can you just
the
repeat?
Mobius loop, right? The Mobius transition state. So because these are, this orbital and this orbital are the ones that are going to connect, and this orbital and this orbital are the ones that are going to connect in this Mobius loop, this supra antra, right?
But why are those connecting? Is it because that is, you said before, like, that's not where the electron is, that's just where the bonding can occur.
Yes, exactly. So because this is a supra antra, which means that one side, it's supra, their one side is the same, right? Supra, bottom. Well, I guess I should have done that in purple, but whatever, supra, right? They're the same versus antra, or rather, I'm sorry, this is like the antra side, right?
No, yeah, and I understood. And then the other one is top, bottom.
Yeah, exactly. Yeah. So that's how they're coming in. So what ends up happening is this energy, as we see here, it has to move through the molecule, through the atom, to switch the energies, move through to switch sides so that it can continue that. So what you see is that you have a pi bond like this, and then you might have a pi bond like this, and then a pi bond like this, because what it's doing is it's moving from the bottom and going to this bottom, and it's switching because the node is like on there, it's switching so that it can come this way, right?
Wait, and for the part where you labeled S and A, wait, aren't they flipped? Or maybe I just am getting that wrong. Because isn't the one that says A, their bottom, isn't that supra?
Wait, where?
On the top, right? On the top where
This?
you were, no, like on
This?
the top. Yeah.
Yep. What about it?
Yeah, so isn't the part that's labeled A supposed to be S and the part that's labeled S supposed to be A?
Where's S and A?
Oh, you just erased it, but it's fine.
Oh, sorry. I thought it was like that's something they
No,
wrote.
sorry, no, it's okay.
No,
It's
no,
okay.
no, that's okay. So with this one, so 6S, like super, like that means that this is a supra. It means that it's on the same side, right? They're
Yeah,
on,
right. So the one you labeled, the green one that's to the left right now.
yes.
And then you labeled the one adjacent to it directly to the right. Yes, aren't those two no, isn't
No,
the
no, I know.
green?
I did that to just to show that they're antra.
Yeah,
So
so but I mean, isn't the
So
green one
supra
and
has to do with are the ends on the same side, right? Versus
yeah.
they're not on the same side.
Yeah, so like the two that are leftmost, the green and the yellow that are leftmost, isn't
Yep.
that supra?
So supra just means like if you look here at this, see how they're saying that this molecule is antrafacial. And they're saying that this molecule is supraficial. And the
Oh
reason,
my gosh, wait, you know what? I'm getting confused because I thought that the super antra thing was between the two p orbitals that are bonding.
oh, like, okay, I get what you're saying. Yeah. No, so it just has to do with where on this, see how this is on top and this is on bottom. Whoops.
No, yeah. So I understand now.
That's what antra means. It
No,
means that
yeah,
they're
I
opposites.
understand. I was thinking that like with
You
the
were thinking that
definition.
this is what defines supra or
Yes,
yeah.
yes.
No.
Okay, yeah. See, this is why this is good to like
Yeah.
discuss this because I was getting that so wrong.
Yes, yeah. So in this case, when they say antra, all that means is that the ends of your whatever's coming together, right? Say you have more this way, right? And so you have this whole thing, and then you've got this here. What antra would mean that both of these were oppositely like this.
Yes,
So that
I
they could,
understand.
so yeah, so like the ends here and here are opposite, and the ends here and here are opposite. So this is antra and this is antra, but because they're both antra, they can come to, because they both have, say, maybe one node or three nodes or five nodes or whatever, but they can both come in with this same molecular orbital
Yeah,
availability.
overlap.
Yes,
Yes.
yes.
I totally got the distinction now. That was
Cool.
yes. Oh my gosh, I'm so excited. Okay.
Yay. Okay. Good. That's good. I'm happy to hear that. Yeah, I know. Yeah, it does,
Okay.
I get it. I get it. Yeah. So that's what the Mobius loop is. The Mobius loop just is like what allows for that addition to happen, because the cycloaddition to happen, because it has this transition state, but not transition state really, but it just has this like like they say, right, it's like similar to the reason why it got its name is, do I even have it on here, is because of the twisted loop, right? So it makes this right here, the Mobius strip. So it has this twist. So this is a good way to look at it, right? Right, this would be your Huckle. It's unbroken, so it's all, these are all on the same side, right? Versus your Mobius loop, there's this break here, because you have this transition between right here, right? Because it goes through the atom on the molecule. So that when it comes through around to the other side, see, they're not on the same orbital. or they're not on the same, you know, bonding, anti-bonding, so they don't make that that space, right?
Yes. Okay.
Um, yeah, and that's where, you know, so like some of this stuff comes in, right? Is like we have these, this is where Huckle, our continuous energy, because we get to split these up here, right? So, but because they're split up in this way, right? That's what makes them higher in energy. So versus when they're like this, you know, in this broken Mobius loop, they're lower in energy. So that's why anything that's 4n versus 4n plus 2. Because of this, if we had plus 2, then it would fill it in here and it would be happy, right?
Yeah. Okay.
Anything else about this one that you were, I know you said you had like a couple questions about it, so.
Actually, can you go to page 8?
Yes, on Aeromess. Where is it? Anti-aromatic. Let me see, what does page 8 even look like?
It has
Application.
a pentane, and then it has the
Right here.
that's the
Oh, this is the bottom of it.
oh no, oh
Wait,
yeah,
wait.
right there, right there. No,
This
no,
stuff?
go up.
Oh, up.
No, go up. Right there.
Okay.
The last example.
This one?
Yeah, I mean it's the continuation of the one from above. They're the same
Oh,
question.
yeah. Okay, okay, okay.
So for this question, I want to go over the paragraph because it says looking at the diene. Do you see that part? It's in the middle of your page. Looking at the
Oh,
diene.
right here. Yeah. Okay, right here.
Looking at the diene, the two hydrogen substituents on the outside are both on the same side in the provided product. This is just like a Diels-Alder reaction. The provided product must have been formed in a suprafacial on the diene. How do you know that?
Okay, so looking at the diene, the two H hydrogen substituents on the outside are both on the same side in the provided product. So the provided product here has these hydrogens. So this hydrogen is also here. Okay, so then it's saying this is just like the Diels-Alder reaction where the provided product so the provided product must have been formed in a Diels-Alder happens, it's allowed because it's doing, you know, superficial on the diene, right? So this one, let me get my pen.
But how do you know that it's doing that?
Okay, so we can go back to like whether it's supra or antra, is that what you mean? Or yeah.
Yeah, let's go over that piece of it, but I thought also I thought I understood that whether something forms or not is depending on if like the reactant on the right, the di or the left, the diene and the whatever it's called, dienophile, the interaction between those, like if one is supra and the other is supra, then it works. And if one is antra and the other one's antra, then it works, right? So when they're just saying that like the product is formed in a suprafacial on the diene, how do they know that that diene is suprafacial and that the product would form? Because isn't it also dependent on if the dienophile is supra or antra? Like, how are they just looking at that one thing and concluding that it's gonna work?
Okay. Yeah, because it's an 8-electron system. So this is specifically talking about, yeah, so we still don't know if this product is allowed or forgiven, or forbidden rather. And to figure out exactly how the reaction occurred, specifically its stereochemistry, supra or antra. So look at the diene. The two hydrogen substituents are on the outside. Both are on the same side in the provided product. Oh, that's what we just read. Okay, so looking at the anion, the two methyl substituents are both on the outside. and are both on the same side in the provided product must have happened superficial. So the provided product, which we still, where's our, okay. So remember our rotatory and conrotatory? So
Yes.
if they're, so disrotatory means they move in the opposite directions. Conrotatory means they move in the same direction. So if these both moved in the same direction, if these both moved in the same directions, that means that this one would point, like this one would go up, for example, this one would go down. This will go up, this will go down. So then they would be opposite of each other, right? But they're not. They're not opposite of each other, right? Versus, whoops, if these guys, these are both pointing out, which is why when we've created, where is it? Oh, here's the methyl. So these are both same side. These are both down, down.
Right.
This is a 4. Oh, but this is an 8 system. Wait a minute, because this should be. Oh, we're trying to figure out if this is forbidden or not. Yeah, because I'm like, this wouldn't even happen. So, right. Like that's why I was so confused, because I'm like, that wouldn't even happen if they were both superficial, because it's an 8 electron system. But that's what you're trying to do. You're trying to figure out if this is allowed or forbidden. So what you're asking is, by looking at this piece and looking at this piece, how do they determine if it's supra or not?
Yes.
Just by stereochemistry. See, for me, I would say, well, if it's
Wait, by stereochemistry, you mean the fact that the methyls are both pointing down?
yeah, isn't that what you asked? Like, how do they know that this is supra from like the hydrogens? Like from the hydrogens being outside of the molecule? Isn't that what you asked or no? Oh, the hydrogens are right there. What am I doing?
Yeah, I basically just asked for that sentence when it says the provided product must have been formed in a suprafacial on the diene.
Yeah, that's what I mean. That's the
Yeah, like,
stereochemistry, right?
okay.
So your
Yeah.
stereochemistry is like, these are both pointing up. They're both on the same side. So for it to have been superficial,
So that's how you know?
disrotatory. So if they're both out and we turn them in the opposite direction, then they would both be up. Versus these are, or they would both be down, right? In this example here, but or that is, I guess, where, but anyway, if we're looking at it up here, right? So this has to do with your conrotatory and your disrotatory. So for this example, we don't typically draw the hydrogen on there, but we need to figure out what the stereochemistry is. So for this example, these are both out, out, right? These are both out, out, and these are both up, up. So if they're on the opposite sides, they're both pointing out, and then on the product, they're both pointing up. That means that they had to have turned in a disrotatory direction. And
Okay.
disrotatory creates supra, right? Supra, or antra, right? But so it has to.
Only for the Huckle one.
No, this doesn't
Or
have
the
anything to do with.
Huckle, whatever
This
it's
doesn't have
called.
anything to do. This concept that I'm explaining right now doesn't necessarily have to do with Huckle or Mobius. How
Oh,
this, how it connects at the end, you'll see, is because a 8 electron system is forbidden with a Huckle system. So that's
yes.
this question is
Understood.
asking, would a Huckle transition state, or what I forget what's exactly is the question. Is the following concerted reaction allowed or forbidden according to the aromatic transition state theory, which is Huckle, right?
Yes. Okay.
So in this case, so because we have to figure out, well, what would, how would this reaction proceed? Well, because of the stereochemistry, the way in which this molecule is oriented as a reactant and as a product, we can see that these are out and these are down, same direction, right? I was doing them the other way, but same direction. So if they're both pointed outward and they're both pointed again in the same direction, either up or down, right? Then that means that they had to have moved in a disrotatory manner. And disrotatory is supra or antra, right? But in this case, because it's two,
Yes.
right? So it's a supra.
Oh,
Yeah. And then the same applies for the other piece of it, right? Same thing. Our methyls are out and now they're both pointed down. So that means that they had to have gone in a disrotatory direction.
yeah. Okay, I see.
So that's what that concept is talking about. And then so to be able, so right here, so it must have been formed 4s, right? It's because there's 4 electrons here that are participating and 4 electrons here that are participating, 2, 4, right?
And just one real quick question on what you just said with the figuring out how many electrons are participating. Do you simply look at and count basically the number of double bonds and lone pairs? Is that how you get that number?
Not necessarily. It's only if they're actually like participating in the reaction, right? Because there might be other double bonds that aren't participating.
So how do you, yeah, so yeah, that's my question. How do you know what's participating and what is not?
Well, because you're doing a cycloaddition. So you know with a cycloaddition that you're trying to create this bond here. And then you would start with your lone pair. So this is 2, 4, because you have to move these electrons away, right?
Right.
6, and then again, same concept. You have to move these electrons away, 8.
It's just in the
You're part of that conjugated system.
it's just on from the last page of like 13 of this section when it
13
had
of arom
yeah or
aromaticity,
no
or
it's not it's section 5 anti-aromaticity and Mobius structures, are they real? And 13 it's like the last part of any of the of this chapter, if you will.
last part of this chapter. Okay, yeah.
Yeah. You oh yeah, it's like all the way down, literally the last page. Yeah, but like, so do you see how the two that are the sp2 hybridized? I did not understand why one of the pairs of those electrons counted and the other didn't.
In which one?
In B and C.
In B and C?
Yeah, it says 6 electrons are participating. Can you just explain to me why
Yeah,
those?
in both of them, you mean?
Yes.
So this has 2 electrons that participate in this one. And then you have 2 and 2, right? So it doesn't actually get
But I don't understand why only those 2 are participating.
well, you wouldn't have it wouldn't participate, both of its electrons wouldn't participate, both sets of non-bonding electrons wouldn't participate in it because it's not going to create, like, the sulfur is not going to create that bond. So and in here, right? So it's going to be planar. Oh, this is just asking like for like planar or not, right? So you're only going to have that 1 electron pair because see how the shape of it, you have like your electrons here, like these electrons, basically is what I'm trying to say. These electrons are not going to participate because it's not in the same. Remember when you start to have multiple pi orbitals, you have this, and then you also have the one that kind of like comes out sideways like this. Like imagine this is like away from this is out of the page, right? So these are all different planes, right? We have this plane here, and then we have this plane here, right? And then we have this plane here, which, forgive my
But
drawing.
like,
so
how do you know that those electrons are going to be in that horizontal orbital, if you will, and not in the one that's pointing down?
you mean like this one here? Because we have
I mean,
Y,
if you
X.
go to letter B in the
Yeah.
planar thing,
Yeah.
do you see where you circled in yellow those
Yep.
electrons?
Yep. These
So,
just won't participate.
right. How do you know that those electrons wouldn't live in the bottom one? Because then they could participate.
Ma'am, do you remember molecular
Oh,
orbitals? What are you talking about?
I get confused.
You can't have 4 electrons living in one orbital.
Yeah. Okay, yeah, I knew that. I just got confused. Okay, but then, so what's the thing? But it seems like, so in the explanation, it seems like the reason why they don't participate is due to it being sp2. That's what it says. sp2 hybridized orbital, not in Huckle loop, 6 electrons. So what is the, like, what property does sp2 have that makes it not participate? Like, are those two things related to each other? I'm not
So this
getting the
has to,
correlation.
yeah, so this one also has to do with like how many bonds that this one will want to make. So sulfur's not going to make 4 bonds, right? Like it's like it's like oxygen. Oxygen's not going to make 3 bonds. It's only going to make 2, right? It's going to hold on to electrons over making another bond. So like sulfur is only going to make those 3 up to those 3 bonds. So
Okay.
sp2, yeah, so they're both sp2, right? So 1, 2, right? Well, then we have 3, but but these, because this is not, this has a positive, this is a positive charge. That's why in this one, it will still be like 6 electrons, right? Even though this has this double bond on here, it will still be these 6 electrons because this one's not going to participate. So you're only going to see this one. Or I'm sorry, this one, this is kind of like a bad drawing, but like these are the ones that participate, not these ones. That's what I was trying to say.
Yeah. Okay.
Yeah.
Okay.
So the ones that are actually like in this, like, so like kind of imagine that they're in this part of the bond, right? And they're reacting in that way, as opposed to like these ones over here are not going to participate, right?
Yeah.
But
No,
these
I
ones
see.
will, these ones will, because of the orbital, right?
Yeah, but doesn't nitrogen only want to make 3
No,
bonds too?
nitrogen will make 4. What?
No, but
Yeah,
doesn't it
no, I mean, yeah, of course, but it will participate in that reaction. Like it's still going to participate in that reaction. So it still has these that it will, because nitrogen will take on, it can take on like a positive, it can more happily take on a positive. So it will donate its electrons to it, right?
Okay, so sulfur is, so it's due to the fact that sulfur is like electronegative and doesn't want to be positive, and if you put those electrons in a bond, it's going to get a positive formal charge.
Right. Like here.
So
Yeah.
what does that have to do with being sp2?
The
I didn't make the correlation between sp2 and why they don't bond
For these ones,
for B and C.
for B
Yeah.
and C. Um, so
Like there must be something special about sp2, like that
yes,
I just
so nitrogen can change from, so sp2s will only participate. Okay, so this has to do with their bonding. Okay, so did I add this in here? Oh, whoops. Let me see if I added this in here, because it kind of has to do with their, do this. Okay, it has to do with their bonding, their orbitals. So let me see, if we back up, I guess I didn't add it. So, okay, so this has to do with their unhybridized, their hybrid. Okay, so it says on page 10, if you look back at it, where does it start? I guess it starts heterocycles. So there's 2 pi bonds. So do you see like the bottom of page 9?
Bottom of page 9. Yeah, I'm
The
one
pyrrole.
sec. Yeah.
So there's 2 pi bonds, two from your pi bond, 2 from your pi bonds, and then 2 non-bonding. So this is a 6 electron conjugated system, right? Because remember, you can still have the conjugated systems like with your electrons. So it says
Yes.
that the nitrogen atom changes hybridization from sp3 to sp2 because it can generate this cyclical Huckle loop containing 6 electrons and be aromatic. Right.
Mhm.
So, and this also has to do with your stereochemistry of your molecule of being planar, right? So if nitrogen is sp2, it must be planar. If the nitrogen was sp3 hybridized, the structure would be non-planar and therefore would have no Huckle loop. So in these examples, it's specifically asking if they would be planar or not. So if planar, each structure would have a Huckle loop, right? So this one's asking about planar and non-planar, right? And so it's we have these, right, to show our how they would work if they were planar or non-planar. Okay, so and then it goes on to talk about oxygen, right? So in furan, so it's sp2 hybridized to allow one and only one of the electron pairs to be conjugated. So one electron pair is conjugated and one electron pair is not conjugated, right? So it's not going to participate, right? So that allows for this 6 Huckle loop, right? 6 electron Huckle loop aromatic to happen. So only one pair of the non-bonding electrons are part of the Huckle loop. Let's remind ourselves, sp2 hybridization really means for oxygen atoms, what it means to look at it from the side. So this has to do with our stereochemistry. Remember that sp2, not stereochemistry, our molecular geometry. sp2 is trigonal planar, right?
Right. Yep.
So so it says that the second pair of non-bonding electrons are in sp2 hybridized atomic orbital. They are at right angles to the conjugated Huckle loop pi systems and are irrelevant, which is what we see here, right? Or I guess you could say what we see here, right?
Yes.
These ones at a right angle, right? That's this. So that's that second. So it's the same idea, right? And they don't have any about, so the base, let's see, it's getting non-bonding electrons into the bond, lowers their energy significantly. So stabilize, has to do with nitrogen. Bronsted base is an example. So in the case of our loops, all atoms are in the same plane. So it really just has to do with the hybridization of like how the hybrid atomic orbitals are used. Do you see that? So the S for sp2 is sigma pi sp2 sigma pi sp2 sigma, non-bonding, right? So that's what this one has to do with, is like, would this participate in the aromatic Huckle, cyclical Huckle loop, right?
Mm-hmm.
I'm trying to see if they have like a sulfur one as like an example other than that, but they don't. But it's the same idea, right? Is that like your sulfurs are not going to, they have those 2 sets. You're only going to do the ones that are in that. So avoids Huckle. So for D, for example, right? Like this one, these electrons are considered part of this system. So you have 2, 4, which avoids a Huckle loop. Oh, it says it right there. So it would be non-planar, right? And this is like also to do with like the strain that you have. So versus these, we have this planar system, right? So that's what that sp2 versus sp3 has to do with. So the sp2 hybridized orbital, these ones would not be in the Huckle loop, right?
Right.
So same with this. So here's 1, 2, and 3. right? But we have this positive charge. So we would just not have these ones in this Huckle loop because we have this double bond here where it's participating. These electrons in a part of this, right? It already has these electrons that are participating in the loop. It's already a part of those pi bonds. So these electrons will not be a part of it because it's in a different pi orbital.
Yeah, okay.
Because planar versus non-planar, your Huckle loop, right? Non-polar.
Yeah, I get it. Like the goal, or I think I understand the goal of a Huckle loop is to form a conjugated system, and
Yes.
all the orbitals have to be parallel to one another.
Yes,
And
exactly.
by nature of the two lone pairs, they are not parallel. They are like they're almost
Yeah.
like they're
They
like
can't be.
yeah, they can't.
Yeah.
I see it now. Okay, that was good.
Yeah. Versus this one, right? Like this is going to be non-planar because we have these 8 that will participate in this. Now, if this had like a double bond here and not here, then it would, right? Then these
Yeah.
electrons could participate in it. It would have these 2 electrons here, but this would make this 6, right?
Yes. Yeah, understood. Okay. Yeah, okay.
Did I copy this on here twice? I did. Oh no, I think I think that's what I did. I accidentally copy and pasted it. Anyway, but yeah. And
Sarah, thank you for the
yeah.
marathon.
Yes, no problem. Oh my God, it's already 2 o'clock. Wow, I didn't even
Yeah, I
realize.
know, I'm sorry.
No, you're fine. You're fine. You're fine. You're fine. No, don't even worry about it. You're welcome. We'll do the other, we'll do the, Dr. Pillai review session on, Wednesday.